It's my great honour to welcome you all.
It is a very prestigious award. It means the world to me.
They have great senses of humour.
I like to reveal parts of history to them, for I love making history come alive.
They are some of the best people that you can come across.
To help them open their hearts.
I always come back to this quote. How can we be role models to learners if we're not learners ourselves?
It's quite useful to get out of our bubbles, not our COVID ones, and sort of see what else is out there.
By sharing best practice, we can see the whole picture. We can see what really matters.
One of the biggest brains around.
It's easy to forget how much has to happen behind the front line.
As a global schools group, Cognita educates over 55,000 students across 12 countries. We're proud to be Wellbeing Partner at this year's Festival of Education, and we want to share the work that we're doing to prioritise children's well-being. This starts with a clear understanding of what well-being is. We looked at the evidence and created a simple Be Well charter that everyone can use day to day. It gives a clear definition of well-being and then focuses on the specific contributors that influence it. Discover our full Be Well charter video and other resources to use with your students and families at cognita.com.
I really try to not look at myself as just a science teacher. I feel like as a teacher, it's very important to help students grow and develop outside of your lessons. A single teacher believing in you and really believing in you. One teacher doing that can have a large impact, but if you have one or two or three all telling you that and really, really believing in it, it makes you feel like you can achieve anything in the world, honestly.
Welcome to this Festival of Education keynote session, part of the annual Festival of Education, taking place online from the 16th to the 30th of June. This year's festival is free for all teachers and educationalists across education in the UK and beyond. This has only been possible thanks to the support of our incredible partners. A huge thank you to our headline partner, Pearson, our festival partners, BBC Bitesize, Cognita and Teach First, our literary festival partner, Bloomsbury Publishing, and our organising partner, Wellington College, the home of the Festival of Education. We'd also like to thank our incredible speakers. Over 200 leading educationalists and thought leaders will be providing sessions at this year's festival. On behalf of the audience and organisers, thank you. It's time to sit back and get set for our upcoming keynote session. If you wish to ask a question during this session, please head over to our Slido page to submit questions and vote for your favourites. Enjoy this Festival of Education keynote session.
Good afternoon, Festival. My name is Derek Richardson. I'm joining you from Pearson. I'm the responsible officer at Pearson, responsible for the standards and quality of all of our qualifications. So I'm really excited, and it's my privilege to introduce one of the biggest speakers of this year's festival. And for me, he really is one of the headliners. Dylan Wiliam is Emeritus Professor of Educational Assessment at University College London. In a varied career, he has taught in inner city schools, directed a large-scale testing programme, served a number of roles in university administration, including Dean of a School of Education, and pursued a research programme focused on supporting teachers to develop their use of assessment in support of learning. Dylan's session today is titled, When Can You Trust Meta-analyses? We're hugely grateful and delighted that Dylan is able to present at this year's festival. So Festival, please welcome Professor Dylan Wiliam.
Thank you, Derek. So in today's presentation, I'm going to try to provide you with a guide to interpreting research findings, and particularly those that are presented in the form of meta-analyses. So in this presentation, I'll just share my screen, and I'll just share my screen now. And what I hope to do is to really get you to understand why meta-analysis is useful, why it's limited in its potential, particularly in education, and how you can make sensible use of meta-analyses in your own work, particularly deciding on priorities for schools, colleges, and other educational institutions. So the outline of the talk, I'm going to start by talking about the Reproducibility project, which you may have heard about, which actually sets the scene very nicely. I'm then going to talk about why a single study is not going to mean very much. I'm going to talk about why synthesizing the results of different studies, which is obviously sensible if one study doesn't mean very much, is very hard everywhere. And I'm going to talk about some particular problems that make it really difficult to do well in education. I will conclude with some recommendations about when you can trust meta-analyses. I'll also briefly discuss when you can trust meta-analyses or syntheses of different meta-analyses. So I'll start with the Reproducibility project led by Brian Nosek in the Open Science Collaboration. So what they tried to do was to take 100 studies published in 3 leading American psychology journals, they're listed there. And the important point about this project, it wasn't a gotcha. They were trying to find out whether these studies would replicate if the replicators conducted the studies as far as possible in exactly the same way as the original authors had done. So they were encouraged to collaborate, share their protocols. And what they actually found was that, as this diagram showed, that very few of the studies replicated. So this diagram shows the original effect size on the horizontal axis. The vertical axis is the replication effect size. And so if all the studies had replicated pretty much as expected with some random variation, you'd have the same number of dots or circles above the diagonal line as below it. And what you can see is that that's not the case. In fact, the replicated effect sizes were much smaller, often not significant. So the red dots are not significant. The blue or teal colored dots are significant. And in fact, many of the studies found not just lack of significance, they found effects of close to 0. And so the conclusion was that the effect sizes they found in the studies were approximately half of those in the original studies. Only approximately half of the results were significant. And only 39% of the results replicated. So this has been cited now as a kind of clarion call to researchers in psychology and in related fields such as education, that we really need to address this replicability or reproducibility crisis. If a research study gets published and people rely on it and it turns out not to be replicable in another situation, we're really likely to make bad decisions about how to direct our efforts. So as Daniel Wiliam reminds us, one study is just one study, folks. The question is, why can one study be so misleading? And John Ioannidis, a professor at Stanford University, in an article in 2005, published a paper called Why Most Published Research Findings Are False. And that paper is openly available. The point he made is that there's two big reasons. One is inadequate statistical power, and the other is what have been called researcher degrees of freedom. And I'll explain each of those in a bit more detail. So why is statistical power so important? Well, there's a number of definitions here from Floyd Bullard, but I'll just stick with the first one. You can look at the slides later if you're interested. I will be posting all these slides in Dropbox. You can download them and use them in your own institution. So the big idea here is that the power of an experiment is the probability that if the effect that you're searching for is real, that you will actually, in the experiment, get a result that is significant. So what's the likelihood of a real effect producing a significant finding? So with a single standard straightforward experiment versus control, depends on what your significance level is, how big the effect is, how big your experiment, and how much noise there is in the outcome variables. So let me actually give you some examples. Let's say we flip a coin 10 times and we get the following results: 7 heads and 3 tails. Can we conclude the coin is biased? Well, it turns out that that actually happens about 17% of the time. About 1 time in 6, 10 coin flips will produce a result as extreme as 7 heads and 3 tails, or 7 tails and 3 heads. If we flip it 20 times and get the same proportions, 14 heads and 6 tails, then that's going to happen by chance around 6% of the time. And the convention is, it's just a convention, the convention is that we set 5% as the threshold. So if the chance of this happening with a fair coin is 5% or less, then we conclude that the coin probably is biased. And if we flip it 30 times and get the same proportion of results, 21 heads, 9 tails, that only will happen about 2% of the time. So by making the experiment larger, we are more likely to be able to detect this effect. So this is how biased the coin is. It's a sort of 7-to-3 proportion, and we need something like 20-something coin flips for the result to be significant. Obviously, we're also more likely to get a significant effect if the coin is more or less biased. That's the magnitude of the effect. So if we get 7 heads and 3 tails, that's 17%. If we actually get 8 heads and 2 tails, we get that about 5.4% of the time. So again, we probably couldn't conclude that the coin is biased. But using our standard 5% threshold, if we get 9 heads and 1 tail, then that will happen about 1% of the time, or the result, that extreme, will happen 1% of the time. And therefore, we probably would, just with 10 coin flips, because the result is so extreme, be able to conclude with a 5% significance level that the coin is biased. So how powerful are most experiments done? Well, one estimate for psychology is that the average psychological experiment yields a significant result if the effect that you're researching is real, about 40% of the time. An estimate that in neuroscience, it's only about 0.2, so only 20% of the experiments that are researching real effects find significant results. And education seems to be roughly similar to psychology. So we're talking about a 40% chance of a particular experiment researching a real effect, producing a result that is significant. Why does this matter? Well, it's much easier to get significant results published. One estimate in health education is that it's 12 times easier to get a result published if it's significant than if it's not significant. And the conclusion of this is only lucky experiments get published. So in other words, the experiments that get published are the ones where things just happen to go right and everything's just worked perfectly. And that means that the ones that get published are probably an overestimate of the ones that actually got done. This is called the file drawer effect. The studies that get published are taken seriously. The ones that are not published because the results weren't significant are still in the researcher's file drawer. And Randall Munroe, who writes under the pseudonym XKCD, makes this point beautifully in a series of cartoons. Jelly beans cause acne, scientists investigate. Well, we found no link between jelly beans and acne because the probability of getting this result by chance was greater than 5%. I hear it's only a certain color that causes it. Okay, so we actually investigate. No link between purple jelly beans and acne, no link between brown jelly beans or pink or blue or teal or salmon or red or turquoise or magenta or yellow, gray or tan, cyan. Whoa, we found a significant link between green jelly beans and acne. And so the headline is green jelly beans linked to acne. Well, that's not a significant result. It is a significant result, but it's not an important result because if you do 20 experiments, and then the chances are you'll get one result that's significant, even though there's nothing going on, because you set a 5% significance level. One other example that I really quite like, this is claimed to be a real experiment. An fMRI scan of an Atlantic salmon was shown 15 photos of humans in social situations for 10 seconds, and the salmon was asked to determine the emotion being displayed. So voxel-wise stats using a GLM, general linear model analysis was used to identify areas of significant blood oxygen level changes. And they're shown in this diagram here, those two spots. One more thing, the salmon was not alive at the time of scanning. So this is a significant result from a dead salmon. So the point is that if you have very low power, then the results that get published are the ones where everything happens to go right. That's a problem. The other problem is now known as the issue of the researcher degrees of freedom, the choices that researchers have. And this is something that Russ Roberts in his econ talk constantly points out. You need to look at what happened in the kitchen when these results were being prepared. And Andrew Gelman has described this as the garden of forking paths after a story by the Argentinian writer Jorge Luis Borges. So one example is data peaking. You do an experiment, you get the result. It's not significant. So what you do is you actually do some more experimentation. You actually extend the experiment. The point is that this is actually now illegitimate because you only took that decision after you saw the non-significant result. So that's a choice you made. But the important point is that then you've actually given yourselves 2 bites of the cherry. You are now heading down the garden of forking paths. The other set of issues that really come under the heading of hypothesizing after results known, or harking, as Norbert Kerr describes it, the choice of methods. So the choice of methods is a choice. And so sometimes you might actually do one method rather than another after you've seen the data. Well, that means that you're more likely to get a significant result. You might look at your data and decide that particular results are outliers. That actually gives you more chance of being successful. You might focus on more or less plausible subgroups. So one particularly important issue in educational research is the researchers find that when they look at the entire data, they find no significant effect. But then what they do is they say, but what happens if we look at only those teachers, for example, who implemented the program with fidelity? And then you find a significant result. The problem with that, of course, is this might have nothing to do with the intervention. It might be that the teachers who implemented the program with fidelity were actually more effective teachers because you've chosen to look at a subgroup, and there's no reason to suggest that subgroup is representative of all the teachers in the study. And that's why there's increasing agreement, first in medicine and now in education, that what we should be doing is what is called intention to treat analyses. So in other words, in medicine, you don't just look at the people for whom the procedure went well. You start by deciding, is this person a suitable candidate for the procedure? And then all the people who were judged as suitable, you look at all the outcomes rather than just the ones where things happen to have gone well. But by actually focusing on more or less plausible subgroups, you're giving yourselves more chance to be successful. And a classic example of this is outcome switching. And this is a huge issue in medical research and in particular education research. In education research, for example, you might say, we're experimenting to find whether this new way of teaching mathematics is more effective. You find no impact on student achievement, but you do find a significant impact on attitude towards mathematics, for example. Fine, but that's outcome switching, because now you've given yourselves two chances to be successful. You can either be successful by improving achievement or by attitudes. And this is actually a major problem in all research areas. So let's look at some examples of where hypothesizing after results known is an issue. So one of my favorite examples comes from the work of Brian Petley, who looks at measurements of the speed of light. So here are some various estimates of the speed of light. And you can see that there seems to be a consensus about the values that were being generated. So that it seems to be converging on a particular point, but then the true value is over there, established in the 1970s. And what he calls this, what Brian Petley calls this, is intellectual phase locking. So if you know that a certain effect is likely to produce a certain experiment is likely to cause a certain effect, then you might check your results if you're finding something very different. And the classic example of this is Millikan and his oil drop experiment, where in his notebooks, he talks about getting good results and less good results. And so the important point is, if you are checking whether you're on the right track by looking at your results, you are in effect hypothesizing after the results are known, which brings in subjectivity and bias. Outcome switching is particularly prevalent in medicine. So Ben Goldacre and his colleagues in the Compare Trials project just looked at the top 5 medical journals, and they looked at all the studies published there over a 5-month period from October 2015 to January 2016. They then compared what was published with the entry of that study that had been proposed or logged when the experiment was started. They found 67 trials. Only 9 of them were perfectly reported. There were 354 outcomes in the experiments that were not reported. And more alarmingly, 357 new outcomes were silently added. That's over 5 per paper. They were adding outcomes they had not said they were going to look for. They gave themselves more chances to be successful. Interestingly, Goldacre and his colleagues followed up by sending letters to the journal editors. 18 of the letters were published out of the 58. 32 were rejected by the editor. So what is interesting is not only is this a problem, but even in medicine, where it's a matter of life and death, there doesn't seem to be much interest in solving this problem. And so we need to be very cautious about results that are published. And that's, again, support for Ioannidis' view that most published research findings are false. It's therefore obvious, it's therefore pretty understandable why it is that people would actually think about looking at lots of different studies, because this really matters. You see, if you just do one test at the 5% level, then obviously, that's an outcome that's likely to happen by chance 5% of the time. But if you do 2 tests, you're giving yourselves 2 bites of the cherry, so you'll get a significant result 10% of the time. If you do 5 statistical tests, you'll get a significant result 23% of the time. If you do 10, you'll get 40. So if you do lots and lots of tests, you will get a significant result. As Ronald Coase, the economist, said, this is an example of torturing the data until it confesses. The idea of doing test after test after test, it completely invalidates the assumptions of null hypothesis significance testing, and the results aren't meaningful. Also important to remember that even when the results are replicable, they may not be generalizable. Again, going back to Daniel Willingham's important point, one study is just one study, folks. This is one of my favorite examples. A parachute used to prevent death and major trauma when jumping from aircraft, a randomized controlled trial. So what they did was they did an experiment where they randomly allocated people to jump from parachutes, from aircraft with or without parachutes. And so the standard examination protocol, 92 aircraft passengers, 23 were agreed to be enrolled, and they were randomized to either jump with or without a parachute. So the intervention was jumping from an airplane or helicopter with a parachute versus an empty backpack. And because people could tell whether the backpack was empty, it wasn't a blind experiment. Okay. So the main outcome measure was composite of death or major traumatic injury. They found that parachute use did not significantly reduce death or major injury. Puzzling, isn't it? Actually, here's a look at the conclusion. The trial was only able to enroll participants on small stationary aircraft on the ground, suggesting cautious extrapolation to high altitude jumps. In other words, the only people who jumped were the people who were actually on the ground. So the point is that when you get people doing what you ask them to do, they may not be representative of all the things you ask people to do, and therefore the findings may be replicable, but not generalizable. Perhaps a less silly example comes from the classic study of class size reduction, the Tennessee STAR study. And it is a really important experiment. Frederick Mosteller, one of America's leading statisticians of the last century, described it as one of the greatest educational experiments ever conducted. So it was a very nicely designed trial. So what they did was they recruited schools where you could actually have teachers and students randomly allocated to either small classes, standard size classes, or standard size classes with an aide, an assistant. And so this was actually maintained from kindergarten through, I think, second grade. And the great thing about this study is that they followed up the participants. So they've actually had follow-up data to see whether these people actually completed high school. So what they found was that the students assigned to the smaller classes were 3 months ahead by the end of second grade, much larger benefit for students at risk of school failure. And Hank Levin and his colleagues showed that the graduation rate from high school for these students in the smaller classes were 11 percentage points higher when these children were 18. So this is really important. This is a really impressive vindication of class size reduction programs. But some caution is needed. First of all, it turned out to be impossible to maintain randomization. So it seems that some parents found out about this experiment, and when they found out that their children were in one of the larger classes, they kind of pressure the school to move them into one of the smaller classes because parents really believe that smaller classes are helpful. And one follow-up study seems to indicate that the children who moved to the smaller classes might have been socially advantaged, pushy middle-class parents, for example. And so therefore, part of the higher achievement could be due to the fact that high-achieving middle-class children were moved from the larger classes to the smaller classes. A more important issue about generalizability is that to participate in this project, each school needed to have 57 children in kindergarten because they wanted to do the within-school randomization. So you needed 22 plus 22 plus 13, 57 students. The trouble, of course, is that some schools didn't have that many. So importantly, rural schools were less likely to have as many students, and therefore the study disproportionately overrepresented students in urban settings. Nothing wrong with that, but generalization to rural settings is problematic. The other thing that's important, and this has really only become clear after this research study was published, only 50 extra teachers were needed to create these smaller classes. And it's quite reasonable to assume that you could find 50 teachers who are as good as the ones you've already got. But when you roll this out to scale, it turns out that teacher recruitment is often an issue. And so in places like in my hometown, where I live in Florida, when the state of Florida reduced class sizes in early primary schools, we needed to employ a lot of extra teachers. And because it's a poor rural area, doing that was actually difficult. So school districts in poor rural areas have been forced to employ people who really probably wouldn't have got a job if there wasn't such a shortage of teachers. So the availability of additional teachers is another issue. And it turns out that the teacher quality effect, in many cases, is larger than the class size effect. So by giving jobs to teachers who are less effective, because you're reducing class size, you may actually reduce student achievement because the class size effect is larger than the class size effect is smaller than the teacher quality effect. It's also important to understand the right kind of theorization about your results. So there's a classics finding in the research literature that when people do a surgical procedure more often, the outcomes are better. And so one study looked at over 200 surgeons producing coronary artery bypass grafts on almost 40,000 patients over a 2-year period in Pennsylvania hospitals. What they found is that the more often a doctor performed the operation per month, the better the outcomes. So on average, a surgeon did 37 of these procedures. So they did roughly 37 per quarter. So 10 a month, once every 3 days. For each extra procedure a surgeon performed per quarter, the mortality rate dropped. And so if they did 1 per weekday, the mortality rate was 2.5%. If it was occasional, once per month, it was 3.3%. So in other words, the mortality rate was about 30% higher if these surgeons did these things just once a month as opposed to once a day. End of story, you might think. Except, turns out, that's not the end of the story. Because what they then did was look at where these surgical procedures were performed. And what they found was that for each extra procedure a surgeon performed at that hospital, the mortality rate dropped. But if they performed additional procedures in different hospitals, the mortality rate did not change. So it turns out not to be a practice effect, as additionally thought, it turns out to be a teamwork effect. And so the really important point about this study is that somebody thought to investigate, does the mortality rate differ according to whether the surgeon is doing these things in the same hospital or a different hospital? Because otherwise you just accept that this is a practice effect. And so because of these single studies, there's now increasing interest in this process called research synthesis. One study is just one study, folks, as Dan Willingham reminds us. So how do we actually find trustworthy conclusions? We combine the results from lots of different studies. And David Goff has pointed out that sometimes the aim is to actually quantify an effect. Sometimes the aim is to make sense of things. So I find this framework that he's produced quite useful. So when Paul Black and I set out to review the research on formative assessment in 1998, what we actually did was not really to figure out an effect size for formative assessment. What we were doing was really exploring. And we actually now realize, retrospectively, because this terminology wasn't around 20 years ago, what we were doing was a configurative review. We were trying to get a sense of the research field. We weren't trying to actually average across all the studies. So not all research synthesis is aimed at finding an effect, but often it's a good idea to find out whether this particular program, this particular treatment, this particular way of teaching is more effective. In that case, you do need an aggregating research synthesis as opposed to a configurative review. And that's why over the last 20, 30 years, there's been real interest in systematic reviews. Rather than just relying on researchers kind of drawing conclusion from the research studies they know about, a systematic review tries to use explicit systematic methods. And in a way, that's really quite important, because the idea is that somebody else can come along behind you and figure out what you did, and then they can decide whether they would come up with the same conclusions. So, for example, when Paul Black and I did our review of formative assessment, one of the things we included in the paper, was the list of all the journals that we had reviewed looking for papers, because we couldn't use keywording, because in education, keywording is not reliable. In places like high temperature superconductivity, you can guarantee that any paper you're interested in will have high temperature superconductivity in the keywords. But when you're looking at formative assessment, it might be responsive teaching, it might be formative assessment, it might be assessment for learning. And so sometimes you just have to go through all the evidence you can find. And the important point is you tell people how you went about that so they can check your findings. So there's a useful set of checklists here of systematic reviews. And these are pretty unexceptionable, clear objectives, a methodology that is reproducible. You identify all relevant studies. You look at the validity of the findings, including the risk of bias, and then you present these results systematically. And so it's important to understand that meta-analysis is not necessarily the same as systematic reviews. So this statement here from Green and colleagues is quite helpful. Many systematic reviews contain meta-analyses. Important to note this because you could actually do a systematic review of studies that include qualitative measures, qualitative research findings. But the idea is meta-analyses provide more precise estimates of the size of the effect of healthcare, for example, than those individual studies. And so there's a quite useful case study that I like to quote on the use of antiarrhythmic drugs after heart attack. So a lot of epidemiological evidence suggested that giving people antiarrhythmic drugs after a heart attack would actually improve outcomes. And it seemed to have worked in animals. It seemed to be supported by the epidemiological evidence and the knowledge of how the physiological systems worked. So Kurt Furberg decided to review all the short-term trials they could find. And so the criteria are listed there, at least 100 enrollees, random assignment, all-cause mortality, not just the one that were attributed to the drugs, had to be reported. And this slide shows the results that he found. So you can see there, the odds of death in the experimental group is given in the middle column. So the Holman and Bergman found that if you were given antiarrhythmic drugs, it seemed to increase the risk of death by 250%. So you were 2.5 times more likely to die if you were in the experimental group than if you were in the control group. And just for ease, I've just put the results that are over 1 in red and those that are below 1 in green. The important point is the 95% confidence interval didn't allow you to conclude anything about any of these studies because all of the 95% confidence intervals included 1. So not very conclusive. So what Furberg reported in 1983 was that the theoretical potential for a preventative or prophylactic effect of antiarrhythmic drugs, excluding beta blockers, in the treatment of coronary patients with ventricular arrhythmias has not been realized. In other words, we haven't yet found evidence that this works. 10 years later, Furberg, in collaboration with a couple of other researchers, actually reviewed all the trials done up to that date. So systematic research, all completed randomized parallel controlled trials, and here's what they found. So here there were far more studies, so I've just listed the drug here and the number of studies and the effect sizes, the odds, the relative risk of death. With a 95% confidence interval, 2 of them were significant, but really it's quite hard to see any pattern, although this seems to be more red than green. What they then did was to use a statistical procedure called the Mantel-Haenszel procedure, which allows you to combine all the results. Effectively, you're seeing other proportions of deaths in the control group and the experimental group the same across all the studies. And what they found was that the use of antiarrhythmic drugs increased the risk of death by 14%. And it's been estimated that the use of these drugs caused more deaths than American soldiers died in the Vietnam War. And the important point is, it was the failure to systematically synthesize these results that led to this really terrible tragedy. And so now there's great interest in these statistical techniques for combining results from different sources to come up with an overall effect, typically through meta-analysis, usually involving a standardized effect size. So the idea of a standardized effect size is you use a metric, a measurement to compare different studies. So let's say I've got a new way of teaching maths, and I want to find out, and I find out my new way of teaching maths is the students getting this new way of teaching maths score 1 point higher than the students taught in the old way. The question is, does that make any sense? Is it a big effect? Well, it depends what your measurement is. If the measurement is the SAT, where the scores range from 200 to 800, it's a tiny effect. If it's American College Testing or ACT effect, it's a much smaller effect. The scores are much more restricted. And if it's the AP calculus test, where the scores range from 1 to 5, then it's a implausibly large effect. So the important point is, you can't just compare scores, you have to standardize them. And the classic way of doing that is to subtract the control group average of the experimental group average and divide by a measure of spread of the population, which typically we use as population standard deviation. And since we never have that, we use an estimate of that. So the important point is that this actually yields a number of problems, which I'm going to list here. I'm going to go through them each in turn. Inappropriate comparisons, the idea that things work better for some people than for others, more discussion of the file draw problem, the fact that often studies vary in their intensity of intervention, how variable the population is, selection of studies, and also whether the measures being used are sensitive to the effects of instruction. So let's go through these in detail. So first of all, inappropriate comparison. So John Hattie has famously produced this barometer of influence where he actually suggests that 0.4 is a kind of benchmark for effect sizes. What he says is that 0.4 is what you get for business as usual. And therefore anything less than 0.4 should be ignored. Well, the crucial thing is, it depends whether it's a net or a gross effect. So for example, when Paul Black and I worked in Kent and in Oxfordshire to help teachers develop their practice of formative assessment, we reported an effect size of 0.32. Now, if you look at Hattie's barometer of influence, you would assume that's basically worse than business as usual, except that the comparison that we made was with teachers doing formative assessment with teachers in the same schools not doing formative assessment, or sometimes the same teacher the previous year not doing formative assessment. So the 0.32 effect size was actually a net effect after having subtracted off the business as usual. So you've got the net effects versus gross effects. And if you actually add these together, thinking that they're comparable, you get very misleading results. You also have to be careful about cross-level comparisons. So for example, one study of teachers working on formative assessment in the United States looked at teachers doing formative assessment in a randomized controlled trial, and they found an effect size of 0.8. But the effect size that they reported was at the level of teachers. So in other words, the teachers' average performance was 0.8 standard deviations higher if they were doing formative assessment than if they were not. And because the correlation of teacher quality with student achievement is about 0.2, at the pupil level, at the student level, that would correspond to an effect size of only 20% of 0.8, i.e. 0.16. So you have to be aware that sometimes effect sizes aren't the effect sizes at the student level, they're the effect sizes at the teacher level. And that means adding them together makes no sense at all. And the other issue, of course, is are you comparing business as usual versus nothing, or the best alternative treatment? So it's widely accepted that in medicine, you've got a new painkiller, you shouldn't compare it with no painkiller, you should compare it with aspirin or paracetamol or something like that. A second issue with meta-analyses is what you might call aptitude-treatment interactions. This dates back to the research in the 50s and 60s on whether some kinds of treatment were more effective for some students than others, some kinds of intervention were more effective. And so it's a useful framework for thinking about studies. And so here's one of my favorites from Esther Duflo and her colleagues, a Nobel Prize-winning economist. So she did a very nice study getting teachers to come to school. So they actually looked at a number of non-formal education centers run in India. And in half of them, approximately, teachers were paid regularly. They were paid 1,000 rupees per calendar month. In the other half, they were paid according to their attendance. And they actually had to submit 2 photographs every day of them taken by a student, of them with their students at the beginning of the school day and at the end of the school day. And if they submitted those 2 with a time-stamped, tamper-proof camera, they got credit for that day. So they got 500 basic salary and then an extra 50 rupees for each day over the 10-day threshold. And it did actually improve teacher attendance from 58% to 79%, and it increased instructional time, and more importantly, it increased student progress. So where teachers were paid bonuses for turning up, students made 25% more progress, which is a great result. But what is disturbing is this has been used as evidence in numbers of policy papers as evidence that paying teachers more improves student achievement. Well, if teachers aren't turning up for school, that may be true. But if teachers are already turning up for school, then there's no evidence that it does. So that's the important point. Incentives may work in some contexts, they won't work in others. You need to be careful that you're not mixing up chalk and cheese. The file draw problem I've mentioned already. It's a huge problem in educational research. I've just modeled it for you here. So if a true effect size is 0.4, then when you actually look at the effect size of the studies that are actually published, if only the significant published studies are published, you'll get an effect size of 0.68. So the true effect size is 0.4, but because the experimental studies are so poorly powered, it's only the ones where you get the just unexpectedly large effect sizes that get published, and so the reported effect sizes way overestimate the true effect size. Now, this is actually easily solved. And in fact, many of the problems I'm going to identify with meta-analysis are routinely discussed by experts in meta-analysis, such as Larry Hedges and Borenstein and others, and they actually talk about how you can control for these problems. So one very clever way of doing this is what's called a funnel plot. And this comes from the book that Larry Hedges and Borenstein have written about how to do meta-analysis. And so here's an example of a plot that shows the size of the effect on the horizontal axis. And they've presented this as a log risk ratio. And the vertical axis is how accurate the results are, basically a proxy for the size of the experiment. And you can see there's probably more results to the right of the middle than the left. And what they actually suggest as a procedure is what they call trim and fill. So you just add in studies to make them balanced. And so you can actually easily detect publication bias by looking for a pattern like that. And you can correct for it. It doesn't solve all the problems, but the point is now you can see, if you look at the two diamonds at the bottom, the two rhombuses there, you've got the white rhombus, which is the reported effect size. The black rhombus is the true effect size once you've corrected for publication bias. So these are quite straightforward things to do, but not all researchers do this. Variation in intervention quality is a huge issue. So obviously, if you do something for a longer period of time, you're more likely to get an effect than if you do it for a shorter period of time. If you're researching class size, does class size reduction work? Well, it probably depends how much you reduce it by. So if you reduce it by 10%, you get a smaller effect than if you reduce it by 20% or 30% or 50% if you're holding teacher quality constant across the different studies. The important point is you need to know how big a reduction it was to actually make sense of it. There's a big literature now on what's called response to intervention. If children aren't thriving on regular whole class teaching, they're taken out into a smaller group for a more intensive group, what's called a tier 2 intervention, smaller group with a teacher. And then if that doesn't work, then you might actually move them into a tier 3 where they have practically one-to-one tuition. So the important point is, how big is the group in tier 2? Is it groups of 4? Is it groups of 8? And how long are they taken out for? 2 weeks, 3 weeks, 4 weeks, 8 weeks? And there's also issues of collateral effects. So when Joe Bowler and I were researching the effects of ability grouping in English secondary schools in the 1990s, we actually showed that although all schools introduced ability grouping at some point, the later they introduced it, year 10 rather than year 9, for example, the later they introduced ability grouping, it seemed that the greater the progress the children made. But now, looking back at that study, it's not clear that the results are that clear cut because we didn't control for the assignment of teachers. So it could be that the fact that we saw more progress in the schools, the fact that in the schools that introduce setting, for example, top sets do better than bottom sets, it might not be to do with anything to do with setting. It might be that the fact that the bottom sets are getting less qualified teachers. So it might not be a setting effect at all. It might be a teacher assignment effect. And because at the time we hadn't understood the impact of teacher quality on student progress, how big these effects were, we didn't even think to control for that. So the important point is sometimes you only find out after the event that something is theoretically relevant. One of the big issues in looking at effect sizes has to do with the fact that, on average, older students are more diverse than younger students. Now, there's some controversy here because some test equating techniques kind of get rid of this difference. But I think there's reasonably broad agreement that some children learn faster than others. John Carroll in the 1960s proposed that a child at the 95th percentile of learning rate would learn 5 times faster than the child at the 5th percentile of learning rate in a class. My own work on the national curriculum in England suggests that the number is somewhere between 3 and 4. But the fact is that some children learn faster than others. And therefore, a logical consequence of that is that the longer you've been on the planet, the more chance that the faster learners have to pull ahead, and the more chance the slower learners have to fall behind. Why does this matter? Because these differences are huge and they affect the effect size calculation. So Bloom and his colleagues looked at the average progress made by students as measured by standardized tests in the US. And they found that for 6-year-olds, 1 year's progress is around about 1.5 standard deviations. For 10-year-olds, it's about 0.4 standard deviations. And by 16, it's about 0.2. So you can see from this graph that John Hattie's figure of 0.4 as the average rate of learning per year is not an unreasonable average. But I would suggest that averaging these numbers doesn't make that much sense. The statistician knows that a person with 1 foot in boiling water and 1 foot in freezing water is not, on average, comfortable. So for me, I think the really important point is age matters. Just as an example, if you increase the rate of learning by 50% through a new way of teaching, maybe one-to-one tutoring, for example, if you did this with 6-year-olds, you'd get an effect size of 0.76. If you did it with 15-year-olds, you get an effect size of 0.1. The same improvement in the rate of learning gives you a much bigger effect size when done with younger children, which obviously affects the meaningfulness of effect sizes. With younger children, you get bigger effect sizes. The other thing to remember is that when you do studies on restricted populations, you'll also get larger effect size estimates. So one conclusion that Paul Black and I drew in our research on formative assessment was formative assessment seemed to be more effective for lower achievers. But if you actually analyze low achievers separately, the denominator in the effect size calculation, the range of achievement, the population standard deviation, is actually smaller, and therefore you're dividing by a smaller number and get a bigger answer. So that could be an artifact of the fact that you're actually not looking at the whole data set. Selection of studies is another huge issue. So Maria Ruiz Primo and Min Lee reviewed 9,000 research papers on feedback in mathematics, science, and technology. And they found that actually most of them weren't relevant to their focus on feedback. They retained 238 relevant papers, and 111 of them actually cited data. They then did a very nice classification of the kinds of feedback involved. So I'm not going to go through these 9 points, but they looked carefully at who provided the feedback, how was the feedback delivered, what was the role of the student, and so on. And so they came up with a very nice typology of feedback studies so they could look to see whether certain kinds of feedback were more effective than others. And the important point is this list of 9 things is driven by careful theorization of what is likely to be important in feedback studies. So one of the things that was really disturbing is that in most of these studies, feedback was a single event lasting minutes. So typically, these studies were done in universities. They reckon that something like 75% of the studies were conducted on university undergraduates. So people were invited into the lab, given a test, given feedback, tested again, and then dismissed. 85% of the studies looking at mathematics, 72% of the studies of science looking at that. Very few of the studies reported reliability of outcome measures. Very few of the studies reported multiple feedback events in a week. Now, that's not necessarily a problem, but if you propose to generalize from these kinds of studies to the kinds of studies that we might want to do in schools with children from the ages of 5 to 16, it's not at all clear that these kinds of findings would generalize. And so one of the problems we have is that a large number of studies done on things that we care about in educational psychology are conducted on university undergraduates. And so it's not at all clear that these studies are actually relevant to students who are much younger. The last issue that I want to talk about, and this really is very hard to get one's head around, but it's to do with the fact that some measures used in research studies are much more sensitive to the effects of teaching than others. This is called sensitivity to instruction. And what's important to remember is this. When you actually design a test, you want it to be reliable. And one of the ways you make a test more reliable is by spreading out the data, stretching out using the whole mark scheme from 0% up to 100%. So let's say we've got a maths test for year 8 students. And we give it to year 7 students and we find that nobody gets the particular question right. And we give it to year 8 students and we find that everybody gets it right. So this question is clearly testing something that teachers are pretty good at teaching in year 8. But that question will never be included in a test for year 7 or year 8 because it has no discrimination in year 7 because everybody gets it wrong. And it has no discrimination for year 8 students because everybody gets it right. So the process of test construction, the process of making tests more reliable, which we want, systematically removes things that teachers are teaching quite well. And so you end up with tests that are sometimes, as Jim Popham has described, little more than IQ tests, because replacing a sensitive item with one that is answered correctly by about half the population actually increases reliability because it helps you spread the scores out. And Maria Ruiz Primo did a very nice study about whether you got different effect sizes with different kinds of outcome measures. So she actually produced quite a nice typology of the outcome measures that we use in studies. So one is just looking at the outcome straight after the teaching of what's in the students' notebooks or a classroom test. What she called a close assessment looks at a very closely related aspect. So if the immediate assessment says what are the number of pendulum swings in 15 seconds, a close assessment would say how much time for 10 swings. What she called a proximal assessment, if the actual study looked at students constructing boats out of paper cups, a proximal assessment would say, what makes bottles float? Distal assessments are those that actually take the same, test the ability to apply it in a slightly different domain, especially when the kinds of problems or the procedures of the materials are differed, and the remote are standardized achievement tests. She then calculated the effect sizes for feedback according to the different kinds of outcome measures used. And what she found is that, she didn't even look at remote and immediate. If you look at the effect sizes for a close assessment, you get an effect size of 1.2. If you used proximal measures, you get an effect size approximately 1/6 as great, 0.2. So in other words, the result you get, the effect size you get, depends on how sensitive the outcome measures that you are using are to the effects you're searching for, the extra student learning. Some outcome measures are sensitive to that, some are not. The important point is, unless you know what kinds of measures you have no business combining these things, and therefore any kind of conclusions you draw will be very, very likely to be invalid, unless, of course, you do what good meta-analysts do, which is to look for moderators of effect. So one of the things that is recommended in meta-analysis is to say, okay, do we get different effect sizes according to this versus that? So you might say, does this work better for boys or for girls? Does it work better for standardized tests versus teacher-produced measures? So you can solve all these problems by doing these moderator analyses, provided the research study reports the things that you care about. Unfortunately, most meta-analyses in education don't have any way of research or don't actually report on the different sensitivities of the different measures. And to be fair, Robert Marzano, as early as 1995, pointed out that you got bigger effect sizes with more sensitive measures, but this still hasn't made its way through to standard practice. So we still don't find in typical meta-analyses any kind of attempt to deal with sensitivity to instruction, which makes the results more problematic. So what does it all mean? Well, strictly speaking, and this might actually sound like a rather bold conclusion, but I don't think it is, effect sizes are justifiable only where they are necessary. You see, if you use the same measure for different experiments, like GCSE grades, average GCSE grades, you would not need an effect size. You only need an effect size when you're using different outcome measures. And unless you know that those outcome measures are equally sensitive to the effects of teaching, those effect sizes are not comparable. So I think we should abandon these effect sizes, and instead we should focus on extra months of learning. And so there's a big debate in psychology and education about the right metrics. Some people say percentile growth, some people say effect sizes. Here's my claim. The only sensible measure is extra months of learning. It's hard to do, but here's where it's the only sensible measure. Any improvement in education manifests itself by improving the rate at which students learn. So basically, it's that. So, just to summarize this so far, some problems are unavoidable in meta-analysis, sensitivity to instruction. Some problems are avoidable. I discussed how we deal with those things. Unfortunately, most meta-analyses, or many meta-analyses in education, don't discuss the unavoidable problems and don't avoid the avoidable ones. Just an example of how important this is, Kvav and her colleagues looked at 15 meta-analyses in psychology, and they actually then, would you get a different result if you only looked at the studies that were pre-registered, they said what they were going to do, and conducted the analysis in different sites? And they found that the average effect sizes were only 1/3 as great as reported in the original analysis. In other words, the true effect size is probably only 1/3 as great as a meta-analysis actually found. So when can you trust meta-analyses? Well, very simple. When the exact nature of the intervention is clear and consistent. So rather than saying cooperative learning, what do they mean by cooperative learning? When publication bias is investigated and ideally corrected. Moderator analysis conducted for all the things you might think might make a difference. Was it pre-registered? Did they control for age? Did they control for sensitivity outcome measures? And then, if those things are controlled for, you can actually trust the meta-analyses. And this is being done. Victoria Sisk and her colleagues did a very nice analysis of the effect of growth mindset interventions, and it's pretty exemplary. So what about meta-analyses? Well, I would say that you can only trust meta-analyses when you can trust all or most of the constituent meta-analyses, and that's basically never. We can go into the Q&A into inappropriate comparisons. The pushback I get is, yeah, but these effects average out. We don't know that, because we don't know that all the experiments that actually got done are a random sample of the ones that might have got done. So, to conclude, I think to look at research, you need to ask 5 questions. Does this solve a problem we have? Remember about the study in India of paying teachers to come to school. Do we know what to do? Does the intervention lay out exactly step by step what we need to do? If we do this, how much faster will our students learn? Don't use effect sizes. Ask for how much more learning per year will we get? What will be the cost in money and in teacher time? And can we implement it here? If you use those 5 questions, I think you'll be able to use research sensibly to help direct your school improvement efforts. Research will never tell you what to do, but research can help you avoid wasting time on things that are likely to have a smaller impact for your students. I'll stop there and hand back to Derek and see if we've got any questions that people want to pick up.
Brilliant. Thank you so much, Dylan. That was really fascinating to see and hear everything that you had said. We have got some questions that have come through. So I'll start with one, which is to say there were several references regarding the quality of teaching. And we wonder, in this capacity, how is quality measured?
It's simply whether students consistently make more progress in some teachers' classrooms than others. And in the best studies, such as those done by the Gates-funded Measures of Effective Teaching project, led by Thomas Kane and his colleagues, they actually moved teachers to different buildings, different schools, teaching different kinds of students, and found that the students make more progress in those teachers' classrooms than in others. So we can't be confident about how big the effect is, because the estimates vary widely, but we are now pretty confident that some teachers are more effective than others. But the interesting thing is, depends what you use. So if you use standardized test scores, some teachers are better at raising standardized test scores. Other teachers are better at raising more authentic measures of achievement. So those effects depend on what kinds of measures of student achievement you're using.
Thanks for that, Dylan. I suppose that might link to the slide you were sharing with us about all improvements of teaching being around the rate of teaching as well, which is quite an interesting way to think about it. The next question links to your question around whether or not your views around the growth mindset and how that works.
Well, so there's been a lot of pushback recently. I've heard people describe growth mindset as the new learning styles, and I think that's simply unfair and wrong. So Victoria Sisk's analysis and her colleagues found an average impact of about 0.08 standard deviations, which some people say, well, it's a tiny effect size. And that goes back to Jacob Cohen's ridiculous advice about classifying effect sizes below 0.3 as small, between 0.3 and 0.87 as medium, and over. I mean, first of all, he was aiming at psychology, and you can't actually interpret effect sizes independent of context. So let's put that in context. Almost all the studies that Sisk and her colleagues reviewed were conducted by children over the age of 10, where 1 year's learning is at most 0.4 standard deviations if you're using standardized tests or teacher semester grades, which most of the studies did. So a 0.08 effect size is actually a 20% or more increase in the rate of learning. And given that most of these interventions took an hour or less, I think it's incredibly important. The other point about growth mindset is this. It's a means to an end, not an end in itself. For me, the main value of growth mindset interventions is to get children more receptive to feedback. If you have a fixed mindset, feedback is unwelcome because it might tell you you're not as smart as you thought you were. If you have a growth mindset, feedback helps you maximize your improvement by focusing your improvement on the things that are most likely to improve you. So I think that you're thinking about that in the context, and David Yeager's work on wise feedback in the US is just exemplary. And he's done some very large scale trials that show that growth mindset interventions delivered online, taking less than an hour, have a substantial impact on student achievement. So any teacher who thinks that growth mindset doesn't help is denying themselves something that has got a proven benefit for their students. And I think you'd be crazy not to try to use it in some way. It's hard to reproduce. Teachers can't change their own students' mindsets very easily, it doesn't appear. But something focused on growth mindset, particularly online interventions, does seem to be very valuable.
Thanks very much for that, Dylan. The questions are really coming in fast now, so I'll try to select some out. Some advice that people might find quite helpful from the festival is, how can we simply measure the effectiveness of an intervention?
I think you can't. It's not simple. So I think that, I mean, one of the things we do, there's trade-offs here, obviously. And one of the things we do in education is we never introduce improvements or innovations in a way that's capable of being researched. So we tend to have, for example, a new way of teaching, and we do it across an entire year group. So there's no prospect of learning from that because you won't know what was the cause. So what I would suggest is that I think schools that are really interested in learning from their experience try to randomize them by, for example, doing a waitlist control group. So, we'll do it for half of this year's sevens, and we'll do it for next year's year sevens, and we'll do it, the other half. We'll do it in year 8, for example. And so the idea is we stagger the introduction of reforms so that we are at least in principle capable of seeing whether that innovation had some effect. So just innovating in a way that is at least in principle possible to learn from, I think would be a big step. But the real problem is it's really hard. It's really hard because in education, the effect sizes are small. Meaningful effect sizes start with a decimal point and a 0. And because schools are so complex, you often need to randomize at the teacher level, not the student level, and maybe even at the school level. So most educator experiments are pretty underpowered. Basically, to really learn from something, you need at least 100 schools. That doesn't mean you give up. What that means is you try to learn and you supplement it with some qualitative analysis by doing interviews with students and seeing if the effects that you're hoping for are there in the attitudes of the students, for example? Are they using the feedback? So just developing that inquiring mind. And the most important principle here is, how could you be wrong? I got these results. I think they mean that this method of teaching, what are they? But what about? But what about the teachers, if the teachers in the experimental group were better than the teachers in the control group? But what about? And if you keep on asking yourself those but what about questions, you will become a very good researcher. Because that's what research is all about, is eliminating all the relevant, plausible but what abouts.
That's really helpful advice. Thank you, Dylan. Well, on the sticking with the theme of good advice, we've had another question come through about the extent to which we can depend on research in education, specifically when it's around services that promise X or Y progress following the use of that service. Have you got any advice for people around that?
Well, I think the tools that I presented in this talk give you basically a toolkit to actually begin to look at these sorts of things. So when people say this produces this kind of impact, well, first of all, try to get the raw data, try to get or at least the evidence about, was this experiment conducted in schools like mine? All a randomized control trial, people talk about the gold standard, but all a randomized control trial tells you is what worked, not what works. So if you recruit people to a study and you randomize them and half of them do it and half of them don't do it, then you're pretty sure, if you get a significant effect, that those who did do it did better than those who didn't do it. But you can't conclude that those results will generalize to those who are not part of the experiment, because the schools that volunteer for experiments are not representative of all schools. So you've always got a selection problem here. And so you need to look at, were the schools that were recruited into this study, whether they were in the control group or the experimental group, similar to our school? Because if they weren't, then your chances of learning something useful are diminished.
That's really helpful advice. Thank you, Dylan. And of course, this is available so people can go back and see your slides as well, which is a really, really helpful tool for people and some great advice. Coming back to the questions around quality of teaching and what informs that, we've had a question come through which is asking about the rate at which students learn versus the depth of understanding of what has been learned, and which is more important and how are they connected?
Basically, I've finessed that question by ducking the issue of what it is we want students to learn. So before you're going to actually work out whether some teachers are better than others, you have to be clear about what it is you want your children to get better at as a result of some teaching. And you have to have some measures of that. So in most of my work, I take no view about what children should be learning. You might be happy with surface level features. You might be really interested in deep understanding. And I'm saying, fine, you just give me what you want to use as an outcome measure, and then we can start doing the research I've been talking about. But none of that can start until you are clear yourself about what it is you want your children to get better at as a result of some time in the classroom with teachers. And so that then everything else falls into place. And as I said, the Gates-funded Measures of Effective Teaching project have shown comprehensively that the correlation of teacher quality with student progress varies radically across different kinds of measures of achievement. So teachers who are good at increasing standardized test scores are often not very good at helping students with more authentic measures of performance.
Thank you, Dylan. Really interesting way to think about it. The last question that we've got that's come through was one linked to early on in your presentation. I recall that you described outcome switching as a problem. And the question is, could you say a little bit more about why reporting unexpected outcomes is a problem?
Right. So if you report unexpected outcomes, you are giving yourselves more chance to be successful. So, if you said, I'm going to use a 5% confidence, 5% significance level. And so if I get a significant result at the 5% level, I'm going to claim this is a significant finding. If you, oh, look, that's an interesting result. And you say, oh, yeah, but the point is that's hypothesizing after results are known. You've given yourselves more chances to be successful. And if you look at 10 different things as possible outcomes, then because of that table I showed you, you haven't really got a 5% significance level at all. You've got a 40% significance level. This will happen almost half the time you find something interesting. And that's why pre-registration of the outcomes as well as the procedures is so important, because it stops you from switching the outcomes. Now, you can actually say, okay, that's interesting, but then you must change your significance level. So if you're going to give yourselves 10 bites of the cherry, you shouldn't be using a 5% level, you should be using a 0.5% level. Because you've given yourselves 10 chances to be successful, so to maintain the standard 5% significance level, you need to have a much stricter criterion for each of the 10 tests you're going to do. And these are sometimes called Bonferroni adjustments, or sometimes called adjustments for multiple comparisons. But good researchers do this all the time. Unfortunately, a lot of people don't do that. And again, it's often not reported in meta-analyses.
That's really good to hear. Thank you very much indeed. We are drawing the session to a close right now because we're running out of time and there are no more questions. It's good to have been able to get through all of those. So on behalf of the festival, Dylan, I wanted to say a huge thank you to you. I've been really interested by everything that you've had to say, and it's great to get the insights and some practical advice. So thank you very much, Festival, for joining this session with Professor Dylan Wiliam. Thank you very much for joining.
You're welcome.
It's my great honour to welcome you all.
It is a very prestigious award. It means the world to me.
They have great senses of humour.
I like to reveal parts of history to them, for I love making history come alive.
They are some of the best people that you can come across.
To help them open their hearts.
I always come back to this quote. How can we be role models to learners if we're not learners ourselves?
It's quite useful to get out of our bubbles, not our COVID ones, and sort of see what else is out there.
By sharing best practice, we can see the whole picture. We can see what really matters.
One of the biggest brains around.
It's easy to forget how much has to happen behind the front line.
As a global schools group, Cognita educates over 55,000 students across 12 countries. We're proud to be Wellbeing Partner at this year's Festival of Education, and we want to share the work that we're doing to prioritise children's well-being. This starts with a clear understanding of what well-being is. We looked at the evidence and created a simple Be Well charter that everyone can use day to day. It gives a clear definition of well-being and then focuses on the specific contributors that influence it. Discover our full Be Well charter video and other resources to use with your students and families at cognita.com.
I really try to not look at myself as just a science teacher. I feel like as a teacher, it's very important to help students grow and develop outside of your lessons. A single teacher believing in you and really believing in you. One teacher doing that can have a large impact, but if you have one or two or three all telling you that and really, really believing in it, it makes you feel like you can achieve anything in the world, honestly.